Okay, so we've derived the Planck function, the B function, and that's the amount of energy permitted per unit time, per unit area of the hot object, per little frequency increment per unit solid angle. And so you could plot it. It's just a function of f. And so here we've graphed it here at 3 different temperatures. It also depends on temperature. So this is a black body at 300 Kelvin. This is at 500. This is 700. And so experimentally, we'll see that that's right. That's what actually emerges. Now, to do this, we had to do some statistical mechanics, some quantum statistics. Why did we need to do that? What was wrong with just classical thermodynamics? In classical thermodynamics, as we've seen, there should be, according to the equipartition theorem, a half kT per mode. And with 2 different vibrational degrees of freedom, that would just be 2 times a half kT, or kT of energy. So let's see what that gives us in terms of energy density. So classically, well, first of all, recall that we had this number when we did our derivation of the Planck function. If instead of that, for the average energy per mode, you have kT, what goes on with that? Well, we still have 2 polarizations, and the number of modes is still the same as it was. We've got to add up all the possible vibrational modes that give us frequencies in this range. You'll recall that was a sphere in n space, and this is r squared of the sphere, and this is dn, the thickness of the sphere. And so adding all of this up over all frequencies, that would be the energy emitted by the hot object. Now notice again, we've got L squared times L, that's L cubed. We'll just bring that over to this side so that we now have an energy density on the left. And then we'll pull the constants out of the frequency integral. It's 8 pi kT over c cubed, c squared times c. And then our integral, we notice, we just get f squared df, which actually diverges. So classical theory runs into a problem. It says that a hot object should emit an infinite amount of energy, which clearly is wrong. So the classical average energy per mode doesn't give the right answer. The Planck energy per mode does. So this classical result is known as the Rayleigh-Jeans law. And it says the energy density should be 8 pi kT over c cubed. Now this is du, so we lose the integral, and it's f squared. So that should be the energy density. But of course, and that's called the Rayleigh-Jeans law, Rj. That one fails, okay? If you plot that one, if you plot du over v, this versus frequency, this is a parabola, right? This is just increasing. You're getting more and more energy as the frequency goes up. At higher and higher and higher frequencies, you're going to get a total energy that diverges. So that one didn't work. What did work, the Planck function, du over v, this is the quantum result. This is the correct result. It's 4 pi over c times the b function, and the b function was 2h f cubed over c squared, and then it's 1 over this e to the hf over kt. That exponential function, subtract 1. And what that gets, what you get from that, is of course the graphs that we showed in those few pages. So it's a function like that. Okay, so the Planck one's in green, the Rayleigh-Jeans, the classical theory, is in blue. Now, the failure of the classical model to explain the radiation coming off a hot object, it was known as the ultraviolet catastrophe. And the resolution to this problem, because clearly there was a problem with classical theory, which required a quantum hypothesis, was more evidence in favor of quantum theory. So this, historically, this problem of the radiation coming off a hot object was an important step in the development of the theory of quantum mechanics. It led support to the quantum hypothesis and the quantum model. And experiments have now shown that the Planck curve is exactly right. If you measure the radiation coming off a hot object, you get exactly this curve. All right, so that's the Rayleigh-Jeans law. That was the failed classical theory. Next, another important law, Wien's law. And this one actually works. This one is based on the Planck function. We're just going to notice that there's a peak in this distribution. That means there's a certain frequency that is, if you like, most likely. Okay? There's a maximum to this. To find that maximum, we're going to differentiate and set equal to 0 the frequency derivative of the Planck function. So we see there's f cubed, and then this is e to the hf over kt. So we will use the quotient rule. First of all, we'll pull out the 2h epsilon, the emissivity, over c squared. And then, so we're going to have the denominator here squared. I'll just be lazy and leave it like that. And then we'll have this same bracket times the derivative of the f cubed, so that is just 3f squared. And then we subtract the numerator, which is f cubed, times the derivative of the denominator. So the derivative of an exponential function is itself, times the derivative of the exponent. So the frequency derivative of the exponent gives us a factor of h over kt. Okay, now the only way that this is going to be 0, the denominator will never be 0, because it's only 0 as t goes to infinity, because then you get e to the 0, which gives you a 0 denominator. So the denominator won't be 0, the numerator could be 0. Let's find the frequency at which that occurs. So this is e to the hf minus kt. We notice there's a common factor of f squared there, so I'm setting the numerator equal to 0. I'm dropping the constants. I'm factoring out the f. So if we pull the f squared out, then we get a 3 left here. 3 times e to the hf over kt, that's the first term. Then there's a 3 times minus 1, that's this term. Taking f squared out of this term in the numerator, we have f left, which joins with this fraction to give this result, times the exponential function. So for the function to be a maximum, that only happens when the numerator is 0. Here's the numerator. So in terms of solutions now, we see that that could be 0 when the frequency itself is 0, or when that big long bracket is 0. And that's going to happen when 3 e to the hf over kt minus hf over kt times e to the hf over kt, when that equals 3. Factoring out this exponential function on the left-hand side, we get this equation here, and we see there's going to be no way that we can solve this equation analytically, because it's sort of a mixed polynomial exponential function. So if we just for a moment call this x, and if we want to go in search of that, then we've got e to the x times 3 minus x is 3. Solving this numerically then, numerical methods, you get a value for x, 2.82. That's where this function on the left side will equal 3. So that then gives us an answer for this x thing, hf over kt, and we rearrange that to get an answer for f. Remember, we're trying to find the frequency peak, so it's going to be kt over h, just times this number that we got from numerical equation solving, 2.8214. So that's the frequency at which the Planck function will peak. So we can calculate there, putting in the value of Planck's constant, which is that's 10 to the minus 34 joule seconds, and the value of the Boltzmann constant, 1.38 times 10 to the power minus 23 joules per Kelvin. So we see the joules will cancel out, and then we get per Kelvin per second out of this. Now don't forget the 2.8214. And then the only thing that we're not going to substitute in is the temperature T, because we're going to see that this most common frequency depends only on the temperature of the hot object. So you work out this number, joules cancels, you get per Kelvin per second, or per second is a hertz. So this number works out to be 5.879 times 10 to the power 10 temperature, and then the units are per second per Kelvin. Well, the per second is a hertz, so hertz comes up here, and 10 to the 9 hertz is a gigahertz. So it's 58.79 gigahertz times the temperature. That will be the peak, the maximum frequency, or the frequency at which the Planck function reaches a maximum. That's Wien's law. The maximum frequency coming off a hot object just depends on the temperature. Okay? So this is the second result we're deriving in our video today. The first one, the RayleighJeans law, was wrong because it was the classical theory of a hot object. Wien's law, which is was derived experimentally, is true, and we've been able to come up with it using our quantum theory as well. So it was first noticed experimentally, and the theory was then backfilled later to show why it had to be true, that the frequency did depend very directly with the temperature. Okay, so for a room temperature object, what is it emitting? So 293 Kelvin is the temperature. So Wien's law says 58.79 gigahertz, 10 to the 9 hertz per Kelvin times the temperature. So we substitute in the room temperature of 293 Kelvin times 10 to the 9 hertz, 293 Kelvin. So the Kelvin cancels. So you end up here at 1.722, and it's times 10 to the power 13 hertz. Now, a convenient unit is a terahertz. That's 10 to the 12. So we see this is 17.22 terahertz. Now that is below the visible range, which makes sense because objects at room temperature, we don't see the heat radiation coming off them, say we do a hot ember in a fire. That's simply because their frequency peak lies below the visible range. We don't see this infrared radiation. A much hotter object like the sun, which it will lie in our visible range, or at least a lot of the sun's radiation lies in our visible range. Let's see where that frequency peak is. So it's 58.79 gigahertz is 10 to the 9. So that's the numerical constant. Then we multiply by the temperature, 5778 Kelvin. The Kelvin cancels, and the number that you get here is 3.39 times 10 to the power 14 hertz. Again, 10 to the 12 is a tera, which leaves two other powers of 10 that we throw over here. And we say this is 339 terahertz. That's very close to the visible range now. And if we actually do a plot of the Planck function at 5778 Kelvin, we see that that makes sense. So the peak is about 330. That's just slightly below the visible range, right? The visible range is about 400 terahertz up to almost 800, right? So all this stuff, this is sun emissions, that's all in the visible. But the peak is just slightly below the visible range. This is in the infrared, okay? So the sun's hot enough, though, that we do see its heat radiation. It lies within our visible range. Okay, so that's our pre-lecture preparatory video for today. RayleighJeans law and Wien's law.